Okay, so as I mentioned last lecture, you have to be careful about your definitions. What do you mean when you say something? Your sentence, your question can be grammatically correct, but as a physicist, we have to be much more precise than just being grammatically correct. Now, in the remaining of this course, we will be talking about particles and particles behaving like waves, and waves behaving like particles, etc. But what do we mean by particle? What do we mean by wave? What's a particle? When I say something is a particle, what do you understand from it? Has a mass. Zero or non-zero. We can talk about a mass. What do you mean by position?
With respect to an observer.
Yeah, okay, with respect to an observer. Good, you are learning. You say, is this a particle? Lots of particles. And, well, what do you mean by lots of particles? What do you have in your mind as a particle? If you call this lots of a particle, what do you have in your... Yes, I heard the answer. It's a small thing. Usually we imagine point particles. Well, basically we understand something of a small size, at most. And if we have a large object, we just say that it's lots of particles. It's not just one particle, it's made up of many, many particles. But, I mean, we will still say that this we will classify as a particle for most practical applications, let's say. What else do particles have? What other properties do they have?
Charge.
Might have charge. What would you like to know about particles? What can you measure about the particles? They have momentum. Well, not necessarily. If there are forces, they don't go on straight lines. They have momentum. They have energy. Well, I mean, let me write it. Might influence other particles. What's a wave? Oscillating. Let's see.
Is it possible to say that particles are discrete? Can you be quantified?
What do you mean by discrete?
I mean, you can be a single particle, and can you be half a particle maybe?
Well, we just, in that case, you just call the half a particle, and the whole particle is two particles. Okay, oscillating, what else? Waves. What other properties do they have?
They have properties such as diffraction or interference.
They show diffraction, interference. What's diffraction?
Çok küçük bir sisten geçen ışığın yayılması gibi.
So is it clear what diffraction is and what interference is? What else?
Coherence source'un coherence source yüzünden screen'de belli olan yani phase yüzünden, phase difference yüzünden yapıcı ve yıkıcı girişim var.
So you basically have, if you are saying that if you have two slits, you send some wave. On the other side, if you put a screen, the amplitude of the wave reaching the screen will have such a shape. Here we have both diffraction and interference. So if you would send particles, what you would expect is that the particles, if those particles that pass through should go straight. Well, they might hit the edges a bit, they will have some kind of a spread, but you will observe those particles over here. And those particles passing through this slit, they will go more or less straight, so you will have lots of particles right across. That's what you would expect. For waves, it doesn't happen. So you see here, right across, you have a large peak, just across the middle where no particle can pass. So essentially, the wave is spreading due to diffraction. And when you get here, the total amplitude of the wave is the sum of the waves. So the waves have this superposition principle, satisfy the superposition. And about their properties, they have wavelength and the frequency. Usually we don't talk about the momentum of waves, or we can talk about the energy stored of the wave. Do they influence each other? Do particles influence waves? Well, you see here, you would say that these slits are made in particles. They do influence waves, so the particles might influence other particles or waves. And similarly, the waves can influence other particles or waves. So if we want to separate these objects, their influence on other things, we cannot really use it as separation between the two. Do all waves oscillate? We said that the waves are oscillating. Do all waves oscillate? So well, let's imagine a string. Infinite one, they will not be absorbed.
I don't think it's not oscillating at first place. It's oscillating for non-moving reference frame, but for moving reference frame, it's not oscillating. So
well, let's stick with one reference frame. So just one example. So we have this string. Just imagine you pull it up, and then push it down. This will create a wave. And that wave will have this shape. And this shape will be moving with some speed v. I wouldn't call this oscillating. All the particles making the string will go up and down. But of course, this wave will not have wavelength. It will not have a frequency. It will not be oscillating, but it will still satisfy the superposition, and it will have interference. Meaning that, for example, if we take this wave, if we send one wave like this, and on the same string we create another wave looking right in the opposite direction, as they are moving towards each other, there will come a point when, let's say, the first wave will reach here. It should originally have this shape. The other shape also reaches the same point, but it should have this shape if there was no other wave. Now, what happens is you just sum the amplitudes, and you would get such a shape for your wave. It will have more or less this shape. And as they are moving even closer, there will come a point where you will have no wave at all. And then afterwards, you will get a wave which will have more or less this shape. And even sometime further, you will get two waves of this shape. So first of all, these also have energy. So waves also have the energy. And the momentum, the waves have momentum. These waves on the string. Let's look at this wave. Does this wave have momentum? What is the direction of the momentum of this wave? In the same direction as the velocity. I will disagree. You see, what is the momentum? Newtonian definition. Mass times the velocity. Right? What is the velocity of this mass over here? This mass is moving downwards. In this region, we have a momentum density pointing downward. This mass is moving upward. So in this half, we have a momentum density which is moving upward. And this momentum density is moving in that direction, not even in the direction of the momentum. But still, it has a weird momentum compared to point particles. It also has a momentum. Imagine it colliding with some mass. You see, let's just imagine that, forget about that thing over here. Imagine there is a mass over here. When this wave reaches the end of the spring, it will just hit it upward. It will transfer a momentum in the upward direction, not in the horizontal direction. So that's also another reason why we say that the momentum density of this wave is vertical. In some half it is downward, in the other half, in this case at least, it's pointing upward. Now the frequency, wavelength, well, as we said in that example, not always have these properties. Those waves that have a definite wavelength and a definite frequency are what we call harmonic waves. And they are simple in the sense that every wave, every linear wave, let's say, we can write in terms of harmonic waves which have a definite frequency and wavelength. They will be just a superposition of waves having various wavelengths and various frequencies. But given a wave, these are also not really the defining properties. Yes?
If the wave is not a linear wave, we don't have superposition?
No. Well, the main characteristic feature of waves that separate them from particles will be diffraction and interference. So those are the things that we call, if something is interfering, then we say that they are waves. In fact, for a long time, do you know the story of Newton and Huygens? Okay. So Newton claimed that light was a particle, made up of particles, but Huygens claimed that no, it's made up of waves. And in fact, because of this disagreement, as far as I know, Newton just destroyed the carrier of Huygens. But then there was the Young's double slit experiment. Basically this experiment. So he just created these double slits, he saw the interference pattern, and that was kind of the last blow to the corpuscular theory of light. So after that, it was definitely proven that light is a wave. And light is what we call an electromagnetic wave. And when Maxwell wrote down his equations, it was kind of the final formal description of light as an electromagnetic wave. So the speed of the wave predicted by Maxwell was equal to the speed of the light that we saw. And these electromagnetic waves basically had the same properties of the visible light that we had, at least given us in a certain frequency. So that was the kind of the conclusion that those waves are the light waves. And the light is electromagnetic. It just has both the electric field in it and the magnetic field. And if you would plot, let's say, the electric wave in this form, and then the magnetic field of the same wave will be perpendicular to it. This is how it will look like. So these are the magnetic field vectors at various points. And this is the electric field vectors at the same points. Just try to think in 3 dimensions. These are perpendicular to each other. And the light is moving in this direction. Sometimes there is a confusion. The light is not going up and down. The light is going along a straight line. But at a given point, the electric field vectors, they are pointing up. Their magnitude is getting smaller, then increasing in the opposite direction. So it's the electric field vectors which is constantly changing direction. And, well, this is a harmonic, almost a harmonic wave. So one thing that we observe about light is what we call the black body radiation. Have you ever observed black body radiation? Sun is almost a black body radiation. Well, if you are cooking, sometimes the grills on the fire, they become red. That is also a black body radiation. And if you could heat it even further, it would first become white hot, and then it will become even blue if you keep heating up. But probably it will melt before becoming blue. But any object that is heated, it just emits light. Now we know from Maxwell theory that everything is made up of charged objects, the nuclei and the electrons which are moving around, and they are accelerating, and since they are accelerating, they should be emitting electromagnetic radiation at various directions, various wavelengths, etc. So, but the origin of that light is somewhat known. And if you have it's essentially any object at temperature T radiates electromagnetic radiation. Now we can also imagine two objects at temperature T. They will both emit radiation and also absorb radiation. So there are electromagnetic radiation going between the two. And you can talk about how much each one of them absorb this electromagnetic radiation and emit how much electromagnetic radiation they emit at a given wavelength and at a given temperature. And similarly for these other objects.
Those are the function of wavelength and temperature.
Also a property of the material. But I mean, in this problem at least we have, you can just restrict your discussion to a particular wavelength. At different wavelengths it might be different, and it might depend on the temperature of the object. It will of course depend on the properties of the object. So this will be different than this one. The emission of the first object will be different than the emission of the second object. But if the system is in thermal equilibrium, meaning that their temperature should not change with time, they are both at the same temperature. So thermodynamics just tells us that if two objects are at the same temperature, you cannot have the flow of heat from one to the other one. So that basically tells us that whatever this object is absorbing, it should also be emitting. Otherwise, it will, if it absorbs more than it emits, it will accumulate more energy, and it will emit less energy, so its energy will increase, which means its temperature will increase. And similarly over here. So essentially, what you have is the emission of one object. The ratio of the emission of one object to the absorption of that object should be equal to the emission of the other objects. Sorry, this is 2. This equality should hold, whatever these two materials are. So although how much an object emits or how much an object absorbs might change from material to material. So here we have two different materials. If you have an object that is in equilibrium, the ratio should be the same for everything. It's a universal function. Of course, it can depend on t, it can depend on lambda, but it cannot depend on the properties of the material. For every material, this ratio should be the same. Then we imagine an idealization. So if we just imagine such a material, meaning that it absorbs everything that falls onto it, then for that material, this ratio will just be equal to its emission, how much it emits at a given frequency, at a given temperature, at a given wavelength, at a given temperature. And if you can calculate that for that idealized object, the emissivity that you calculate will be equal to this ratio for every object. So first we have to create this object. So we have to imagine, well, since this is universal, by the way, since this ratio is universal, what you obtain as the emissivity for this object is independent of how you create that object. This object that absorbs all the light that falls onto it. So we will imagine the easiest way to materialize such an object, to realize this object, is just imagine a cavity, an empty box with a hole. And let's just imagine that the walls are made up of a material which is made from an absorptive material that doesn't reflect much light, it just absorbs most of it. So if you imagine a light entering this hole, well, most of it will be absorbed there. If not, some of it will reflect, it will be absorbed over here. Anything that remains will be reflected and it will be absorbed here, and so on. So none of that light can get out. So what is the black body in this picture? No. You see, the black body is this one. The hole. Because it is the hole that absorbs all the light falling onto it. What is behind is just a way of realizing the black body. You know, so for example, for the sun, the surface of the sun is the black body. Okay, so if you want to study, but this is just the realization of the black body, it's the hole. If you want to calculate how much it emits, basically it will not emit what is incident on it, it will be absorbed, but inside there will be electromagnetic radiation. And there will be some of that electromagnetic radiation inside, which is created due to the interaction of the material making the wall. You see the wall, the material making the inside of the wall, it has a temperature, so it constantly emits also. Not as the black body spectrum, but nevertheless it does emit some radiation. Then the question is, what are the properties of the electromagnetic radiation inside this cavity? Once we can determine the properties of the electromagnetic radiation inside the cavity, we can determine how much of it escapes. But that will be the electromagnetic radiation emitted by the hole. So that is since, you see, what we did was, since that ratio is universal, for the same for everything, it doesn't matter how we realize the black body. It shouldn't matter how we realize the black body. And here, the way we realized it is by just putting a cavity behind the hole. So basically, this hole, it absorbs all the light that falls onto it. And, well, due to the way it is realized, it should be also emitting radiation, because inside there will be some radiation due to the walls. But the emitted radiation by the black body is independent of the properties of the walls itself, because it should be universal. Now let's study this radiation inside the cavity. Then later on, we will see how much of it escapes through the hole. That will give me my black body radiation. Okay, so let's start with strings. You see, eventually what I would like to do is I would like to calculate how much electromagnetic radiation it emits per wavelength. So I have to also take that into account, various wavelengths and various frequencies. Now let's imagine a string, a one-dimensional problem. On this string, I can create various waves. I can create a wave that has this shape, or I can create a wave that has this shape, or I can create a wave that has this shape. Okay, just imagine it. Fill in the gaps. And this shape, well, it goes to infinity. Right, so this green one just goes up. There's one node over here, another 0 over here, 2, and the third one. If you count the endpoints, you have 0 over here, 1, 2, 3, 4. The first one doesn't have any zeros. This is called the fundamental mode. The first harmonic is the red one. It just has 1 0 between the endpoints. The second harmonic, the green one, it just has 1, 2 zeros. And the third harmonic is the blue one, 1, 2, 3 zeros along the line. And in fact, you can just imagine infinitely many of them. So these are all called different modes existing on the string. And they have different wavelengths. And then you can ask the question, how many modes? They have different frequencies, different wavelengths. Then you can ask the question, how many modes exist between the frequencies nu and nu plus d nu. Well, you see, as you increase the harmonics, you are basically increasing the frequencies. Not for the first few, but eventually the various frequencies come so close to each other, they almost make a continuum of frequencies. And then you can, if you give me a large enough frequency and then ask me how many such modes exist between these two frequencies, that would be a valid question. Now, let's go back to the cavity. I can ask basically the same question over there. Inside the cavity, I can talk about electromagnetic waves. And then I can ask the question, how many different modes of these electromagnetic waves exist between two frequencies, nu and nu plus d nu. Did you calculate this in 221? Well, I also will not calculate it. I will just write it down because it won't be really irrelevant for the further discussion. The answer is just, there is the volume. There is the 8 pi nu squared d nu over c cubed. Huh? Okay, I mean, if you have calculated it, that's fine. Just go over it if you want to remember it. If you don't, well, just, this is the answer. As I said, it won't be so relevant for your conceptual understanding. Just, we know that there is such a number. And the exact form, I mean, it won't, even that will not be so important. But that's the form of the number of waves. So if you talk about the number of modes per volume, let me call it the n. This is just 8 pi over c cubed nu squared d nu. So that number over there is also independent of v, so I can just talk about the number of modes per volume. Just divide by v. So we know the number. Well, temperature is essentially just the random motion of objects. It can be particles, electrons, or it can even be the electromagnetic waves. So you see here, since the wall has some temperature, it is constantly oscillating. The charges, the electrons, and the nuclei making the wall, they're also constantly oscillating. They are doing accelerated motion, so they are emitting these electromagnetic radiation. They will be emitting some of the energy due to their random motion and give it to the electromagnetic waves. And of course, electromagnetic waves in the cavity will hit the electrons and the nuclei and transfer some of the energy back to the electrons and the positive and negative charges making wall. And what we call the equilibrium is that, just imagine I'm a charged object. As I'm accelerating back and forth, I'm emitting some of my energy. And then all around me, there are electromagnetic radiations. They are also constantly hitting me, influencing me in a sense, and transferring some of the energy back to me. So when the equilibrium is reached, on the average, I just gain as much energy as I lose. So nothing, on the macroscopic level, nothing really changes. So that's what we call equilibrium. Now, there is a theorem that we call the equipartition theorem. Yes?
For that, I did not really understand why you asked how many nodes exist between frequencies. I mean, mu and mu plus d.
Now is the answer. So equipartition theorem tells us that the thermal energy of every degree of freedom is some constant multiplied by the temp T, which is the absolute temperature, divided by 2. Well, what this degree of freedom means is, let's say if you have any oscillator, the energy of the oscillator can be written as p squared over 2m plus 1 over 2 m omega squared x squared. This is called 1 degree of freedom. This is called the 2nd degree of freedom. A more precise meaning would be the squared terms. Well, if you write the energy of the electromagnetic waves, or the energy density. Do you remember the energy density of electric and magnetic wave fields? This is the energy density. Well, you have the squared terms, 1 degree of freedom, 2 degree of freedom. Here you have 1 degree of freedom, 2 degree of freedom. So equipartition theorem would tell us that for the electromagnetic waves, for each mode, the energy of electromagnetic wave has energy T over 2 plus KB T over 2 KB times T. Each mode will have that much energy. Now I have the number of modes. I have the energy of each mode. Now I can write down the total energy per unit volume. In the electromagnetic radiation, for frequencies between nu and nu plus d nu, let me call du, this is equal to 8 pi nu squared d nu over c squared c cubed. This is the number of modes. The energy of each mode is k times t. So what are the possible frequencies of electromagnetic waves? Any limits that you know? They can have any frequency. If this is the energy density per frequency, you just sum all the frequencies to get the total energy. What is the integral of this from 0 to infinity? Infinite. So there's something wrong. This is what's called the ultraviolet cutoff, a catastrophe. Why ultraviolet? Well, large frequency means the ultraviolet region of the spectrum. So if what we had done over here was correct, then in the electromagnetic radiation in the cavity, we should have infinite amount of energy, which obviously doesn't happen. And if we have infinite amount of energy in the cavity, even if a very small fraction of it escapes, the emissivity of the black body should be infinite. But what we observe is du over d nu the observed spectrum has such a shape. This is the observed spectrum. There is very few emission at very low frequencies. There is also very few emission at very high frequencies. Most of the emission is within some range in between. Now, this nu squared law is essentially here. At small nu's, they match, but then you have the catastrophe. It fails at larger frequencies. And until Planck, we didn't have the answer why. Well, I mean, even Planck didn't really answer why. but he just managed to describe it. And we will continue with that on Monday. Any questions before you go? Okay, see you on Monday.